Hi, everybody. So, we're picking up in section 12 of the textbook. So, the first 11 sections are kind of just a basic review of set theory and things like induction and operations on sets and stuff like that. So, that's where the numbering will come from. So, we're starting off with the definition of a topological space. So, these came out of studying the properties of Euclidean space, so Rn, and its subsets, and the properties of continuous maps. So I'm assuming you guys have you've had some exposure to this kind of thing either through like 421 or 521 or maybe 341, all those kind of classes. So I'm assuming you've seen continuity in some sense before, more than like the original like calculus 1 definition. So that's kind of our vague starting point. And that brings us to something. Fuck off. Sorry, excuse me. Forgot to turn my notifications off. It brings us to our first definition for what a topological space is. So, it consists of two things. So it consists of a set, let's say X, and something called a topology, which is a collection of subsets. Which I'll call tau. Such that, what? So this collection tau satisfies the following three properties. Maybe I'll write 1. So the empty set and all of X are always going to be inside tau. Arbitrary unions of subsets, so arbitrary unions of elements in tau are in tau. Maybe I'll say that this means if, say, I have some collection U sub I all inside tau, it implies the union over all these U sub I is a subset of tau. Is in tau. And tau is closed under finite unions. Finite intersections. Wow. My brain is not here. Finite intersections of elements in tau are in tau. And so if this collection tau satisfies those three things, we call the pair X, tau a topological space. And we call the elements of this collection tau the open subsets. So, where maybe you've seen some basics like maybe like metric spaces in analysis 1, a topological space sort of has open sets whatever we say they are, as long as they satisfy these three properties. The open sets are kind of whatever we declare them to be. A main example kind of throughout the entire course will be the real line. And tau will be, these are sort of, in some sense, generated by open intervals. Where, A and B are kind of any two positively extended real numbers. And I'll go over what I mean by generated in a following video. In some sense, every open inside X with this thing called, I should maybe say this is called the standard topology. Standard metric topology. Every open in this topology is in some sense a union of things of this form. This class in general will be quite abstract, and so it's really useful to have kind of a bunch of examples in your pocket at any given time. I like the real line because you've seen it 1,000 times in like calculus or advanced calculus or linear algebra. The real line and Rn in general, it's a really kind of nice familiar type of thing. Similarly, you can kind of get dumb examples. Dumb in the sense that you get them no matter what kind of set you have. So, another example. Any set X can be given two topologies. Oops, can't pluralize things. So there's the discrete topology. I'm gonna give this a green color. So this topology is where I declare every subset of X to be open. In this case, it's the same thing as setting tau as the power set of X. It's a good exercise to check that this choice will satisfy these three criteria. It's kind of trivial in the sense that if tau consists of every possible subset of X, well, your basic kind of operations of sets won't take you outside of that. The other kind of stupid topology you can give to any subset or any set is the, well, we call it the trivial topology. So in the first thing, when we talk about the discrete topology, we said every subset was open. Our kind of criteria for a topological space, the only things that we actually always need to have are the empty set and X. The other things are just criteria, are constraints on those open sets. So the trivial topology is where we say that the only subsets of X that are open are the empty set and all of X itself. Where the only subsets that are open are the empty set and X itself. Sometimes we call this one the indiscrete topology. So these are just kind of silly little things to regard any possible set as topological space in some kind of topology. Let's do maybe one or two more examples. So let's take say X consists of 3 elements, A, B, and C, which I will picture as 3 points. Can you list all possible topologies on X? So given that a topology will consist of some collection of subsets of X, we know that there are probably, the range of possible topologies I can give on this would be, maybe I should actually say this right now. In another video coming up, we'll talk about a way to kind of compare topologies. But clearly this one has the most possible subsets I can endow a space with, right? It consists of every possible subset. Whereas this one consists of really the bare minimum number of open subsets I can give a space. So any topology on a given set sort of interpolates between these two things. It'll have fewer or more open subsets. So how many different topologies can I give the set with 3 elements? Well, I need to always contain everything. I always have to have nothing and everything. But I also could do something like, maybe this is the only subset that's open besides that. Likewise, I could do something where maybe this is the only subset that's open. And if I added in this one, I'd have to have their union as well. So now this looks like empty set, all of X, A, C. So the second criterion says I have to have their union as well. So this is a topology. Just to try to work it out for yourself, it's useful to try to figure out every single topology on this thing. I think this is actually done in the book, but it's just kind of fun to try out on your own. Let's see. Let's maybe do one more to leave you with. Another topology on the real line. This is called the finite complement topology. So I'll denote this by tau sub f. So I will define this topology as a subset U is open in this topology if and only if its complement R minus U is either finite or all of the real line. So as an exercise, I want you guys to show that this is the topology. This isn't something I'm going to collect. It's just kind of a useful little thing to do on your own. Show this is a topology. in order to do that, you have to show that this collection of subsets satisfies these three things. All right. See you in the next video.